All right, last one. I'm going to do 6 and 7 in one video. So section six is about capacitors. And capacitors are a circuit component. I showed you a couple in class, but we will definitely be seeing them more as we go through the next unit, which is circuits. But because it's an actual component, it has a physical makeup of area, distance between, and whatever materials put in between. So capacitor looks like two plates. They can be circular, they can be square, rectangular, and each of the plates has an area. So the area would be here, and this would be our A in our equation. They are distance D apart, and depending on what is in between, we would have a kappa. However, if it doesn't state anything at all, kappa is assumed to be 1, which is the dielectric constant of space or of air. It's 1.003. So either way, we could just assume that it's 1 if it doesn't give us a specific material. Okay, and then epsilon naught is a constant permeativity of free space, and it's 8.85 times 10 to the negative 12th. So when we go ahead and hook up a battery to this, if we hook up, one of the power sources I had in class, and we have that turned up to 12 volts, and we connect it to a capacitor, well, one plate will become positive 12 volts, the other will become 0 volts, giving us a potential difference from the negative plate to the positive plate of 12 volts. Almost as soon as we turn it on, although there is a calculatable amount of time that it would take to charge it, but the charge will be stored. Then, once it's stored, we could actually disconnect the battery, and it is going to keep the charges stored on the plates. Then we can go ahead and actually take these plates and we can change the area. We can make it larger or smaller. And we could do the same with the other side. Well, we would have to do the same to the other side. We wouldn't do less. We would change them both simultaneously and making them larger or smaller. But what's not going to happen is the amount of charge stored won't change. We could also change the distance between them. But because this is true, because of conservation of charge, we can't just lose charge just because we've moved the plates, which is a little shady because you'd have to touch it. But let's just pretend in an ideal world where we could move the plates without making any connection with them. Then what will happen is the capacitance of the plates will change. And again, just a capacitance is measured in farads. Oh. And again, it depends on how much it's made up of. And then capacitance is equal to the amount of charge over the potential difference. But if it has the same amount of charge, so the charge is held constant, we want to know what happens. A lot of times they'll ask you what happens to potential energy. Let's just solve it for potential energy. We have Q over C then. If this stays constant, and this is equal to kappa epsilon naught A over D, then if we increase the area, well, we would increase the capacitance, which would decrease the amount of voltage, the potential difference on the plates. If I were to increase the distance between them, make them larger separated, then that would decrease the capacitance, which would increase the amount of potential. I could also change what's in between. Instead of having a kappa of 1, I could have a kappa of 2. If I increase the kappa, then I increase the capacitance and therefore decrease the delta V, as you can hopefully imagine from there. All right, cool. Let's move on to conservation of electric potential energy. Okay, conservation of energy applies to all types of energy. If something loses potential energy, it gains kinetic energy. Okay, and we will see this on a molecular level as we move to nuclear physics at the end of the year. But delta K is equal to, right, If it loses potential energy, it gains kinetic energy. So the gain in kinetic energy, delta K, is equal to the negative of delta U. It's whatever delta U loses. So we have delta U. We also have this equation, delta U is equal to Q times delta V. So the change in potential energy is equal to Q delta V. And we could combine these two equations to solve for delta K. So the change in kinetic energy is negative Q delta V. So we could even get something more. It might say, what's the final speed of the electron? So you'd have 1/2 mv final squared minus 1/2 mv initial squared is equal to negative Q delta V. And then you might have to put in for the potential V final minus V initial. Not sure what the problem is going to give you. Sometimes they don't say anything about potential. They're like, find the final speed. We don't know potential. So what you would do is you would use 1/2 mv final squared minus 1/2 mv naught squared is equal to, and you would do the rest of this equation. I'm just going to literally copy and paste it here, and that would be what we would use. We'd have the, actually, let me go through how I got that, because we would have the negative change in potential. So we'd have this as a side swipe would be negative U final minus U initial, or U initial minus U final. So when we would do this, we'd have 1/2 mvf squared minus 1/2 mv naught squared is equal to U initial, which is K Q1 Q2 over R initial minus K Q1 Q2 over R final. Okay. And I'm just going to try to figure out how to move that. All right. So there we go. Good luck.